Hello everyone, I welcome you all to the first lecture of this particular course. As you know that the title of this course is Essentials of Oxidation, Reduction and CC bond formation application in organic synthesis. Now to start with, I would like to give a brief introduction to organic synthesis, importance of selectivity and basics of oxidation of alcohols and development of sulfur based oxidations to start. In the organic synthesis that we generally talk about involves the synthesis of natural products or any other non-natural target molecule of importance which have biological importance, or synthesis of some materials or synthesis from any other angle. So, this is what is organic synthesis. Generally synthesis consists of some steps that involve the usage of different types of reactions and reagents and sometimes of course rearrangements. Now these individual steps are also classified as synthetic methods. These synthetic methods involve, as I said, many steps. Now each step can be involving an oxidation, reduction and or CC bond forming reaction, or also an rearrangement. The rearrangement can involve acid, base or light or heat, or even a reagent. This course deals with a variety of important and modern methods for such synthetic methods, with special emphasis on selectivity, mechanism and stereochemistry, and then application in organic synthesis. Now if you look at the natural products, you know many of these natural products already. Say we have terpenes, terpenoids, alkaloids, steroids and many more. So we know that the terpenes are compounds that consist of isoprene, whereas terpenoids are a class of secondary metabolites which are derived from terpenes and will have some cyclic groups and oxygen. Let us take some examples of terpenes. Of course we know that there are monoterpenes, there are diterpenes, then sesquiterpenes and triterpenes, etc. A few examples of them are like here, like this is a monoterpene which is myrcene, then of course we have geraniol of this kind. Of course if the double bond here would be having the CH2OH group pointing below, that means it is trans to the methyl group, then that will be nerol. Then we have carbon, of course here there is an asymmetric center, then of course we have camphor. So there are many such type of molecules which are classified as terpenes. Then we have an example of terpenoid. Now this is a very interesting molecule which is called as Taxol. It is an anti-cancer molecule, it is a very important anti-cancer molecule. The structure of Taxol is like this, it is one of the natural products isolated from a tree called yew tree, and as you can see that there are 3 rings here, fourth one is a oxygen containing ring, then of course we have side chain here. So particular molecule has a number of asymmetric centers. This also has a side chain which has 2 asymmetric centers. That means the synthesis of this entire molecule is quite complicated, not only complicated but needs to be made in optically pure form. But since it is a very important anti-cancer molecule, a lot of work has been done, a lot of synthesis has been reported, some total synthesis and some partial or semi-synthesis. Now artemisinin is an anti-malarial molecule which structure is like this. Now as you can see that it has 3 basic rings, but at the same time there is a bridge here having a peroxide bond. Again it is a very difficult molecule to synthesize, but then many derivatives of these Taxol and artemisinin have been synthesized and assessed for their biological activity. The commercially applicable synthesis of Taxol is very difficult. Therefore, semi-synthetic route to Taxol has been basically utilized. Since isolation of the Taxol from natural source gives only a very small amount of the product, that is the Taxol. As you can see, 100-year-old tree gives only 300 milligrams of Taxol. So you can imagine how you have to grow a tree for 100 years and then you can at the most get 300 milligrams of the molecule, that is Taxol. At the same time, as I mentioned, that the structure of the Taxol molecule which is shown here is very complicated, and therefore total synthesis, that means synthesis starting from a very easily available starting material, is very difficult because it will involve a large number of steps. And therefore the semi-synthetic route has been developed, which is now from this particular molecule which is naturally available. It is called 10-D-acetylbacatine. Now as you can see that this particular acetate group is present in the Taxol molecule, whereas if you compare the structure of this 10-D-acetylbacatine with this particular part here, then you can say that 10-D-acetylbacatine is a starting material for the synthesis of Taxol, and it has no acetyl group at the 10th position. Now this 10-D-acetylbacatine has been isolated in abundance from Himalayan or European yew tree, which is called Taxus baccata, and it gives 1 gram from 1 kilogram of the leaves of this tree, that is Himalayan or European yew tree. So it is much easier to isolate about 1 gram of such a molecule from 1 kilogram of the leaf and then convert into the Taxol molecule. So if we start with this naturally occurring 10-D-acetylbacatine, the semi-synthesis would involve chemoselective acetylation. That means this particular hydroxy group has to be acetylated, otherwise rest of the things are there except the side chain here. So we have to do the chemoselective acetylation at this particular position, and then we need to introduce a side chain. Now already there is a hydroxy group here. So now that hydroxy group has to be converted to this particular side chain which has 2 asymmetric centers. That means we have to make sure that we attach the side chain to this hydroxy group with appropriate stereochemistry and also absolute configuration. So this attachment has to be done. Now you can see that first of all we have to make sure that we introduce the acetyl group at this particular position, and then the remaining 3 hydroxy groups are still there, to which At this particular position we have to make sure that we attach the side chain. So, attachment of the side chain is also a very challenging task. So, there is a scope for synthetic endeavors even after having obtained this particular 10-D-acetylbacatine. Now, we look at alkaloids. There are many alkaloids and they are all naturally occurring organic nitrogen containing bases. For example, this morphine, which has these 5 rings attached to it and a nitrogen here. Similarly, we have this nicotine, which contains these 2 rings. One of them is of course pyridine ring and the other is pyrrolidine ring. Then we have this papaverine, which has these aromatic structures attached to each other, and then we have this strychnine. Now, these are 4 types of alkaloids that I have shown here, but then there are many of them. For example, yohimbine, reserpine and vinblastine, vincristine, there are many such alkaloids which are naturally occurring and they are all biologically important. Now, there are steroids. These are man-made version of chemicals known as hormones, which are present naturally in our body. The hormones which are present in our body play a very important role. For example, testosterone has a structure like this, which is a male sex hormone. Then we have this progesterone, which is a female sex hormone. Then we have cholesterol, which is structurally quite similar, as you can see, and we know that cholesterol is bad for health if it is in large quantity, but is required for the body because then these hormones are actually biosynthesized. Now, similarly, we have estradiol, which is important from both male as well as female sex hormones point of view. As you can see that these hormones or the steroid type of skeletons have 4 rings, A, B, C and D. The A, B and C rings are 6 membered and 4th ring is 5 membered ring. As you can see also that the junctions are trans oriented and that is the common feature in all the cases. Therefore, synthesis of these steroid molecules or the hormones becomes very important. Now, we have other set of molecules which are called as prostaglandins. They are a group of physiologically active lipid compounds called eicosanoids, and they exhibit a lot of different types of hormone like effects. The structure of prostaglandins is somewhat like this. This is one example, but there are many similar type of prostaglandins. A common feature in all the prostaglandins is that it contains a 5-membered ring with substitutions which are contiguously like this as shown here. There are 2 side chains and there is either a hydroxy or a ketone and a hydroxy group here, and the side chains would have of course different double bonds and different hydroxy groups, and at the end there is a carboxylic acid group. Now, these are all very important molecules and they are not very stable molecules and synthesis becomes very challenging. However, a lot of synthetic efforts have been reported in the literature and synthesis for many of these compounds have been improvised and thus involving shorter steps to procure these molecules. There are also enzyme inhibitors of different kinds, which basically are molecules that inhibit the actions of certain undesired enzymes. For example, this Tamiflu which is oseltamivir, is actually a drug or an enzyme inhibitor against swine flu. So, that means it inhibits the enzymes of the virus which is causing the swine flu. Now, there are many pheromones which are called as insect pheromones. These are all chemical agents secreted by insects as sexual attractors. That means male insects will have certain pheromones. The smell of that will attract the female insects, and likewise female insects will have pheromones which will attract the males. So, now what happens is when in certain fields or certain agricultural lands, when there are different kinds of insects which are present and spoiling the field, then that becomes a problem. For example, this particular compound is isolated from female insects of the orange wheat blossom midge. That means this compound is isolated from the female insects which remain close to the wheat and spoil the wheat. And therefore, if we take this particular molecule and synthesize and put it in the field where wheat is grown, then since this is isolated from female insects, and if we are keeping this in a corner of the field, then all the males will be attracted towards this particular compound, and then with a small amount of insecticides you can kill the male insects and not spoil the wheat. Likewise, if we isolate the pheromone from the male insects and synthesize and keep it in the field where this wheat is grown, then all the females will be attracted towards that male insect pheromone, and then of course we can spray the insecticide and kill all the female insects. So, basically these are all molecules which can attract the female or male insects depending on which one we are using, and of course instead of spraying the insecticide over the entire field and spoiling the wheat in this particular case, and thus we can avoid spoiling the wheat. Now, there are synthesis of various kinds of materials like polymers, solar cells, semiconductors that require organic synthesis. Now, organic synthesis of course of a target molecule, whether it is a natural product or a non-natural product, would involve a number of steps. Say if we start with a starting material like A and then go to the target molecule with different kinds of intermediate steps. Now, each step in this particular endeavor would need a reagent or a combination of reagents, and of course then it allows a reaction to carry out. Of course, as I mentioned earlier, it can also be a rearrangement, but it requires a reagent or a set of reagents or certain conditions. So, basically synthesis of a target molecule is actually composed of a number of steps. Say for example, if we start with cyclopentadiene and react with an alpha beta unsaturated ketone like methylvinyl ketone, then either with the help of heat or a Lewis acid we can carry out this Diels order reaction to form this bicyclic molecule, which can be written up like this. As we can see that it has a double bond which can be functionalized or cleaved. Then it has a carbonyl group, and of course there is a alpha hydrogen next to the carbonyl, and there are 3 hydrogens here which are alpha 2 carbonyl group here, and therefore they are activated hydrogens and can be functionalized. So, depending on what the target molecule is, we can carry out different reactions on this particular bicyclic molecule, because it has a potential to functionalize double bond, functionalize ketone, functionalize alpha positions of the ketone. So, obviously one can carry out several steps in between. Likewise, if we start with this particular molecule, which is a bicyclic molecule having an aromatic ring, of course we can have different substitutions on the aromatic ring depending on what is the target molecule, but just to show what steps could it involve is we can do the benzylic oxidation here to go to the corresponding ketone. Then we can functionalize the alpha position of the ketone to the introduction of an R group here, and then we can introduce a double bond. This is further functionalization. We can reduce the ketone to the alcohol in a stereoselective fashion, or if it is required then in an enantiomer selective fashion. Then now we are still left out with a double bond here and then R group. Now depending on what R group is, we can then functionalize the hydroxy group here, the double bond here, part of the R group here, and of course reach eventually to the target molecule. So it means that we can start with a molecule like this and go to the target molecule like this with several different steps. So these are just two examples of how the synthesis can be done of a target molecule starting from a small simple molecule like here cyclopentadiene or something like this here. So it involves a number of steps, and each step, as I mentioned earlier, is of course a synthetic method. Now development of synthetic methods therefore involves development of reagents and reactions and synthons. Development of reagents, that means we need to develop reagents which are of general use or a specific use. Then we have different reactions using those reagents which we can improvise or develop new reactions. And what is called as synthon. What is a synthon? Basically synthon is a synthetic intermediate. Say for example, if we start with a molecule like this, which can be easily prepared from say D-mannitol or maybe from many other sources, it is a chiral aldehyde, it is optically pure aldehyde. It is a 1,2 protected diol having a aldehyde moiety at this particular position. So one can start with this, it is a synthetic intermediate and can be converted to the target molecule. Likewise, if we have an enone of this kind which has an X group here, that can be an ester or SO2R or NO2 or a cyano, anything that we can put it here, or even an aldehyde. And then that becomes a very important molecule which is a synthon or which is a synthetic intermediate. Now the individual steps in organic synthesis of a target molecule can make use of these reagents, reactions and synthons, but then we also need to address selectivity. Now we have chemoselectivity, regioselectivity and stereoselectivity. So if we have a molecule like this which has two different ketones, as you can see this is a saturated ketone and this is an unsaturated ketone. So if we do a reaction on this and allow this particular ketone to remain unaffected, or do a reaction on this particular ketone and let this ketone be unaffected, then this is a chemoselective reaction. Now in this particular ketone, when there is a methyl group on the left side and there is no substitution on the right side, then of course if we carry out the formation of an enol silyl ether by removing this proton here, then this is a regioselective deprotonation and regioselective formation of an enol silyl ether. On the other hand, if we deprotonate on the right side and let the enol silyl ether be made in this way, then of course also this is a regioselective enol silyl ether preparation. So, these are the examples of regioselectivity. Then of course, we have stereoselectivity, where we can have enantio and diastereoselectivity. For example, if we start with a ketone like this, which is a prochiral ketone, and when we reduce it, and we can get a mixture of two enantiomers which are mirror images, but if we can have reaction conditions in such a way that we get only one of the enantiomers as the major product, then of course we call it as an enantioselective reaction. In a similar fashion, if we start with a double bond like this, which is a kind of prochiral double bond, and do dihydroxylation. So, if we do cis dihydroxylation, we get these two molecules which are mirror images of each other, and if we do trans dihydroxylation, then of course we get these two molecules which are again mirror images of each other. So, if 1 and 2 are mirror images of each other, and 3 and 4 are mirror images of each other, then if a mixture of 1 and 2, which is a 50-50 mixture, that is enantiomers, if this mixture is formed in major amount, that means if these compounds are formed in major amount than this, that means dihydroxylation is specifically cis dihydroxylation, then we call that this is an example of diastereoselectivity. That means these are formed in major amount and this is formed in minor amount, that means is example of a diastereoselectivity. In a similar fashion, if we do the hydrogenation of this double bond, then we can get these 4 types of molecules, again cis or say trans hydrogenation. If one of these 4 is formed as a major product, then of course we will call that as enantioselective reaction and also a diastereoselective reaction. Now we go to the last part of it, of today's lecture, and which will be then carried on to the next class, is now to see how oxidations can be carried out. Now in all the oxidations that we are going to discuss, or reductions or CC bond formations that we are going to discuss, we will be basically talking about mechanism, stereochemistry, because that becomes very important to exploit for further developments. Now suppose we carry out an oxidation of an alcohol with say chromic acid. So we would get an intermediate of this kind. So because the alcohol here reacts with the electrophilic chromium 6 species, which leads to the formation of this particular chromate ester. Now it can undergo cleavage of this kind to lead to the formation of an aldehyde, either by the removal of the proton by base which is present in the medium like water, or it can undergo it through a 5-member transition state like this to form aldehyde and release chromium 4 species. If this aldehyde reacts with water, then you get this geminal diol, which then can undergo oxidation to form the corresponding carboxylic acid. Of course, the chromium 4 and chromium 6 species can combine to form chromium 5 species. Now the mechanism of this reaction, whether it is an intermolecular like this, where base like water takes up the proton in this particular fashion to release aldehyde, or whether it involves a 5-membered intramolecular transition state of this kind to remove the chromium species and release aldehyde, is something that needs to be debated. It is difficult in this particular case to assess whether it is intermolecular or intramolecular, because oxidation occurs fast and therefore it is not easy to find out whether the reaction is proceeding in this particular fashion or in this particular fashion. But it becomes apparent when we do various kinds of sulfur base oxidations, which we will discuss in the next class. So, we will stop it here today and then start sulfur based oxidations in the next class. Till then, you take care of this particular lecture, whatever I have taught today, and then we will continue in the next class. Thank you and bye.